So we now move on to chapter 17. And in this chapter, we're going to be looking at a lot of the things that we looked at in chapter 16, but we're going to step up the complexity just a little bit. It's a little bit challenging, so give yourself plenty of time to work on this, and you should do fine. So the first thing that we want to mention is something that we refer to as the common ion effect. And the common ion effect is essentially this. And I'll read it out here. So whenever a weak electrolyte and a strong electrolyte containing a common ion are together in solution, the weak electrolyte ionizes less than if it were alone in solution. So what that means is, well, to illustrate what that means, we're going to do number 15 on the in-class assignment. So we're just going to switch over here to the in-class assignment and do number 15. So we'll start here. We've got calculate the percent ionization of 0.0075 molar butanoic acid. Now, I know the formula for butanoic acid, but if you don't know the formula for butanoic acid, one thing you can do is just write HA as our acid. So butanoic acid is going to dissociate some amount in water, and it will give us the hydronium ion, and the conjugate base of butanoic acid, and the conjugate base of butanoic acid we're going to find is called butanoate, but I'm just going to put A- there. All right, this will be a concentration table, so ICE. And this is essentially just like a chapter 16 problem that we have been working on. So here we've got our initial concentration of 0.0075. The water we can ignore. The initial concentration of hydronium and the conjugate base are both going to be 0. This is going to decrease by x, so 0.0075 minus x. These will increase by x. So at this point, this should look pretty familiar. And then our Ka value is equal to hydronium times the conjugate base divided by the butanoic acid. And we were given in the problem the value of Ka, which is 1.5 times 10 to the negative 5. All right. Well, now that we've got the values at equilibrium in terms of x, and we've got our expression, we're going to put those values into that expression. So here we'll just say that 1.5 times 10 to the negative 5 is equal to x squared over 0.0075 minus x. Now, just like before, we want to determine, is it okay to neglect x? And we'll find here it is just okay to neglect x. So I'll go ahead and do the math here. 0.0075. We'll divide that by the 1.5 times 10 to the negative 5. And you see that gives us 500. Well, 500 is definitely greater than 400, so we can neglect x. All right, so we're going to neglect that value of x. Well, once we do that, we will then get x squared is equal to 0.0075 times 1.5 times 10 to the negative 5. So now we'll multiply those out and take the square root, so 0.0075 times 1.5 times 10 to the negative 5, and we'll take the square root of that, and so the square root of our answer, and that gives us 3.35. We're just going to call that 3.4. So x is equal to 3.4 times 10 to the negative 4 molar. Now, in this particular problem, we're not looking for the pH, so we don't need to take the negative log here, although we could easily do that. What we're going to be doing here is we're getting the percent ionization. And our percent ionization is equal to our change, which is our hydronium ion concentration. But one way to think about it is it's X divided by the initial concentration of the acid times 100. When we put that into the expressions, we get 3.4 times 10 to the negative 4 over 0.0075 times 100. And the answer that we get there is 4.5%. So 4.5%. So what that means is that 4.5% of the butanoic acid molecules are dissociated at any given time. So now what we want to do is we want to look at a common ion. So here it says calculate the percentage of the same concentration of butanoic acid, so 0.0075, but this solution contains 0.085 molar sodium butanoate. Well, sodium butanoate is a strong electrolyte, and butanoate is an ion in common with this weak electrolyte. So really what this means is that initial concentration of butanoate ion isn't going to be 0 like it is here. It's going to be 0.085. So let's go ahead and put those values in. So HA, H2O, hydronium, and the conjugate base. Initial change equilibrium. So 0.0075 minus X is 0.0075. Water we can ignore. Here, this is 0, but again, butanoate, instead of being 0, is 0.085. So 0.085. This will be plus X, X, 0.085 plus X. All right, now we've already got the expression here, so I'm just going to write 1.5 times 10 to the negative 5 is equal to X times 0.085 plus X, and then down in the denominator, this is supposed to be minus X, 0.0075 minus X. All right, now if X is small compared to 0.0075, which it was because it was 4.5%, then that means it's also small compared to 0.085. And we'll find that when we have X on both the bottom and on the top, that we can neglect them both. So we can neglect X, and we will neglect this X. Now, in case you're wondering, like, where does the madness end? I mean, can we neglect this X? And the answer is no. We can only neglect X if we're subtracting it from or adding it to a number that is much larger. Okay, so now that we've got that, we'll come back over here and we'll say 1.5 times 10 to the negative 5 is equal to X times 0.085 over 0.0075. And we'll solve this for X. So X is equal to 0.0075 times 1.5 times 10 to the negative 5 over 0.085. And now that we have that, we can multiply that out. So 0.0075 times 1.5 times 10 to the negative 5 and divide by 0.085. And that gives us a value of X that is equal to 1.3 times 10 to the negative 6 molar. Here, of course, we're not trying to find the pH. We're trying to find the percent ionization. So our percent ionization is going to be X divided by the initial concentration of our acid. So 1.3 times 10 to the negative 6 divided by 0.085. And then multiply by 100 to make it a percentage. So we'll do 1.3 times 10 to the negative 6 and divide that by 0.085 and then multiply by oh, I got the wrong number down here in the denominator. Let me fix that real quick. That's supposed to be 0.0075. So 0.75. So let me try that again here. So 1.3 times 10 to the negative 6 and divide that by 0.0075, and that gives us we've got to multiply by 100. 0.017%. So this is the common ion effect. By itself, the acid was dissociated by 4.5%. When we had an ion in common, the percent ionization went down by 3 orders of magnitude, or 2 orders of magnitude. So it went down by a huge amount. That is the common ion effect, and that's really the whole point of this chapter, is looking at the common ion effect. So let me show you another one of these. All right, so I'm going to show you another one of one without and one with the common ion, and we're going to kind of go through the steps so that you're able to solve these, that you're able to come up with a plan on solving these. So here, this is actually one that we saw in chapter 16. Calculate the pH and the percent ionization of a solution that is 0.30 molar acetic acid, or 0.30 moles of acetic acid and enough water to make 1 liter. So we have the concentration of acetic acid and we have the Ka. Here is the equilibrium reaction. When acetic acid dissolves in water, it dissociates some to give us hydronium ion and the conjugate base, which is the acetate ion. As far as setting up an ice table for this, the initial concentration of our acid is going to be 0.30, because it's 0.30 divided by 1, and then these two things are going to be 0. So 0.30, 0 and 0. The concentration of this will decrease by x, just as a reminder that the coefficient of x is the same as the coefficient of the chemical in the balanced equation. These two will increase by x, and that gives us the values 0.30 minus x, x, and x. We're going to put those into the expression for Ka. So here is our expression for Ka. And again, we did this exact problem in chapter 16, so I'm not going to go into this in great detail, but we know that it's okay to neglect x, because if we take this 0.30 and divide by 1.8 times 10 to the negative 5, we get a number greater than 400. In fact, the number, I just punched it in my calculator, the number we get is like 16,666. So we know that it's okay to neglect x. So here we neglect that x, and again we're just saying that x is small compared to 0.30. And then we can cross multiply, take the square root of that value, and that gives us our value for x. X here is the concentration of the hydronium ion. Right? That if you go back and look at the table, you will see that that is true. We take the negative log of that number, and that will give us the pH. The pH here is 2.64, and that gives us a percent ionization of 0.77%. Again, we did this exact problem in chapter 16, so this should look familiar. Okay, so 0.77%. And by the way, when this number is less than 5%, that tells us that we were correct in neglecting X. All right, well, now we want to look at how it is that we solve common ion effect problems. And we just did one a little bit ago on number 15 on the in-class assignment. And so we want to come up with a logical plan to do this. The first thing is identify the common ion, the strong electrolyte, and the weak electrolyte. And often this is pretty obvious what the common ion, the strong electrolyte, and the weak electrolyte are. You want to write out the equilibrium reaction for the weak electrolyte. So you'll write out that equilibrium reaction for that weak electrolyte. Then we're going to set up our concentration table, and we'll use, for our initial concentration of the strong electrolyte, we're going to use that as the concentration for our common ion in the ice table. In the last example that we did, we used the concentration of the sodium butanoate as the concentration for our common ion, which was butanoate. All right, well, we're going to do the same thing on a problem here in just a moment. And then solve the problem. And solving the problem usually involves neglecting X. So let's go ahead and look at a problem with the common ion effect. So calculate the pH and the percent ionization of a solution with 0.30 molar acetic acid and 0.30 moles of sodium acetate in enough water to make 1 liter of solution. The 1 liter makes it real convenient because the concentration is going to be 0.30 molar and 0.30 molar. So, that makes that pretty easy. Again, here is our equilibrium equation. And writing out the concentration table, the main thing that is going to be different here is that our initial concentration of the acetate, which is our conjugate base, isn't 0. Here, the initial concentration is 0.3. So 0.3, ignore water because it's the solvent. Hydronium is 0, and then this is 0.3. So this will decrease by X, and these two will increase by X. So we'll get 0.30 minus X, X, and 0.30 plus X. When we put these values into our expression for Ka, we're going again, here's our Ka value. We'll get X times 0.30 plus X and 0.30 minus X. Now, of course, if we can neglect X when we subtract it from 0.30, then it's going to be perfectly fine to neglect X when we add it to 0.30. And so all we're saying here is that X is so small, it doesn't really affect these values. So here we're going to neglect both the X in the denominator and the one up in the numerator. Again, we can never neglect this X. That would be bad. If we neglected that, we would have nothing to solve for. So now that we neglected those X, this becomes this. Well, of course, 0.30 divided by 0.30 comes out to 1. So X is equal to 1.8 times 10 to the negative 5. Well, X is the concentration of hydronium ion. So the concentration of hydronium ion is that. Negative log of that is going to give us our pH. And that's a pH of 4.74. Well, now we want to figure out the percent ionization. So we'll take X and divide by the original concentration of the acid, which was 0.30. So 1.5 times 10 to the negative 5 divided by 0.30 times 100. And that gives us 0.060%. Now, we compare that to what we just saw on the one where we didn't have the common ion. And on that one, our pH was 2.64, which is, that's significantly lower. But the big difference here is that percent ionization. In the other problem, it was 0.77%, but here it is 0.0060%. Well, that's 2 orders of magnitude difference in the percent ionization. That is a huge decrease in percent ionization. Okay, so now we want to look at number 13, and number 13 is going to help us transition from this section to talking about the next section, and the next section is going to be talking about buffer solutions. So let's switch over to number 13. So here on number 13, we've got, it says use the information from Appendix D, and that using the information from Appendix D means we're going to need to look up the Ka value for propionic acid. So use the information from Appendix D to calculate the pH of a solution that is 0.060 molar in potassium propionate and 0.085 molar in propionic acid. Okay, well, first thing, let's write out the equilibrium equation, or let's identify what the weak electrolyte and the strong electrolyte are. So our weak electrolyte is going to be propionic acid, that's a weak acid, and potassium propionate will be our strong electrolyte. Our ion in common is the propionate ion, the C3H5O2. So that is our common ion that we are going to be looking at. So let's go ahead and write that out. H. Okay, we want to put our initial concentrations. Our initial concentration of propionic acid is 0.085. Water we can ignore. Hydronium ion here is 0, and our propionate ion is 0.060. This will decrease by x, so we'll get 0.085 minus x, and then these will increase by x. So x and 0.060 plus x. Well, now that we've got those values in terms of x, we're going to write out the Ka expression, so the equilibrium constant expression. It's the concentration of hydronium times the concentration of the propionate ion, so C3H5O2 minus, divided by the concentration of HC3H5O2. Now, I have already looked up the value for this, but you will be able to find it on Appendix D1. And the value here is 1.3 times 10 to the negative 5. So that is our Ka value. So 1.3 times 10 to the negative 5 is equal to x times 0.060 plus x divided by 0.085 minus x. Just like what we had done before, we are going to neglect x. If you do the math and check it, you'll see that it is okay to neglect x. And in fact, you have a little bit more leeway here when it comes to neglecting x. So we're going to neglect the x that's both up in the numerator and the one that is down here in the denominator. So now that we have neglected those x's, we can write this out as 1.3 times 10 to the negative 5 is equal to x times 0.060 over 0.085. And now we will solve for x. 0.085, 1.3 times 10 to the negative 5, and 0.060. And so now it's just a matter of punching those numbers into our calculator. So 0.085 times 1.3 times 10 to the negative 5, and then we will divide that by 0.060. And you'll see the number that we get there is 1.8. I am going to go ahead and write down what seems like a ridiculous number of significant figures here. I'm going to write down 1.8417 times 10 to the negative 5. And the reason that I'm writing down way too many significant figures here is because I want to show you what happens when we carry the number through and what that means when we talk about buffers in the next part of this chapter. All right, so there we go. That is our hydronium ion concentration. And so that means that our pH is equal to the negative log of the 1.8417 times 10 to the negative 5. I'm just going to leave the number in the calculator. So negative log of our answer, and you'll see it comes out to 4.73. 4.73. So that is our pH. So in the next part of in our next video, we're going to be talking about buffer solutions. So that'll be section 17.2. We'll be talking about buffer solutions.